Hi everyone, I'm Chen. Today I will present a laboratory investigation of multiple controls on fault stability and rupture dynamics. We first consider a multiple complicated form of rate and state-dependent friction in autothermal conditions. The shear stress is along a frictional fracture is determined by the normal stress, frictional properties, load point velocity, reference frictional coefficient, and the state variable. The fault stability and rupture styles are controlled by the frictional and the geometrical properties of faults. These parameters can be combined into two dimensional parameters, the Dietrich-Riemann rise number RU and the RB number. The RU number is the stiffening ratio of critical rheological stiffness and system stiffness, and it's associated with the characteristic Euclidean size. The RB number is the ratio of frictional properties that control the dynamic and static stretch drops. We conducted a series of directional experiments on smooth fault in polycarbonate in a directional setup. This setup consists of two plates, the fixed plate and the drying plate. The normal load pressed them together and the shear load is applied on the drying plate to make it slide along the fracture. The AE sensors are used to monitor the acoustic emission during the seismic event. In various step experiments, we assess the frictional parameters A, B, and L, as well as the stiffness K and Kc as a function of load point velocity and a constant normal stress. We can see that the character weakening distance L increases with the load point velocity, but the RU, the stiffening ratio, decreases with the load point velocity, especially the RB shows a systematic variation from 0.3 to 0.15. We then conduct 4 experiments at a load point velocities of 20, 50, 100, and 200 micrometer per second. The normal stress decreased from 2 to 0.6 megapascal with the same interval. With the decrease of normal stress, we can observe a spectrum of slip behaviors from stick snip to stable sliding. In stick snip cycles, the recurrence time and the stretch drop are constant. But for the period multiplying cycles and the chaotic cycles, the recurrence time and the stretch drop are not constant. The experimental results show that the fault dynamics are controlled by the normal stress and the load point velocity. As the normal stress and the load point velocity can change the RU and RB, so we can see that the fault dynamics are controlled by the RU and RB. We illustrate the multiple controls on fault stability and rupture dynamics use a two-dimensional phase diagram formed by the n-dimensional parameters RU and RB. The ratio of previous to subsequent inter-event times in a sequence of 10 events is used to capture the recurrence patterns that take place at various coordinates in this space. The experimental results show that the full spectrum of slip behaviors can occur at all load point velocities, but the domain boundary between stick snip, period multiplying, and chaotic cycles are different for different load point velocities. But for the transition to stable sliding seems independent of RB number. It occurs at around RU equal 1. We finally highlight the period multiplying cycles, and it occurs and a low constant normal stress of 1.5 megapascal at all load point velocities. As the load point velocity is increased from 20 to 200 micrometer per second, we can see that the RB decreased from 0.3 to 0.15, and the recurrence pattern evolves from the period multiplying cycles to almost the periodic cycle, because the recurrence time ratio evolves from 2 to 1 to almost 1. The experimental results show that the frictional behaviors is controlled by at least 2 parameters RU and RB. So we can see that the fault dynamics can be controlled by multiple controls, such as RU and RB,